Great. All right. Let's see today's deal here. Count the number of complete components. You're given an integer n. There's an undirected graph with n vertices numbered from 0 to n minus 1. Okay. So each node is connected to. Okay. Each node, and there's at most. And okay. Anyways. You're given a 2D array edges where edges of I is A, B denotes that there is this an undirected edge connecting vertices A and B. Right? Return the number of complete connected components. So those are basically ice islands is how I think about it. All the nodes are somehow traversable to each other. But what is complete? Connecting component is a subgraph of a graph in which there exists a path between two vertices. No vertex of the subgraph shares an edge with a vertex outside the subgraph. That's fine. It's like an island. And then a connected component is said to be complete if there exists an edge between every pairs of its vertices. Okay. Straightforward enough, I think. So for graphs, first you want to do for graphs, first make a mapping data structure. Generally, it's going to be either 2D array or default a default dictionary of list. Here, because we're dealing with something where it's numerical and it's a very fixed amount, we'll use a default a 2D array. As nodes here are labeled with fixed numbers in a range, use 2D array. So the index, so each node has an array or 1D array within the 2D array that denotes its neighbors. Where row is node, where rows are the neighbor nodes of a row index. Okay, so let's go ahead and first create the graph. So let's say the graph is going to be a list, and each element is a list for each element k in the range of the number of nodes, and then for each edge in the graph. Actually, it's probably easier to say node xy for, so each edge which is going to be having an xy, I guess I could use AB. Fine, AB. XY has maybe some input-output connotations. So it's going to be the graph at A append element B, and the graph at B append element A. Here, since it's undirected, it goes both ways. So anytime you see A, it needs to be added to the neighbors of B, and B added to neighbors of A. Although if it was the case that it was directed, then you would only do one of those two. Probably the graph A append B. And then let's go ahead and just double check that this works. And returned. Edges is a 2D array of tuples, no? Oh, I see, whoops. That's not the syntax. For each index in the edges array, edges at I is an AB tuple. Okay. Index in the range of the length of edges. Yeah, edges is not just a. The issue there was I couldn't assume that all the arrays only had 2 elements, even though that's the case. So it couldn't actually traverse it that way. Let's say AB is edges at I at this index. Is this gonna work? Because it's not really tuple. All right, I'll check to see if that works. Okay. Not sure about that. Okay. So what this is saying here is the graph has 0 is connected to 1 and 2, 1 is connected to 0, 2, 2 is connected to 0, 1, 3 is connected to 4, 4 is connected to 3, and 5 is not connected at all, even though there is a 5th node. And that is aligned with that. Okay. So that's the graph mapping, and now just to figure out where your connected components are. So I guess the simplest way is just to detect which islands exist. The simplest way is to detect which islands exist. And what's the result? The number of connected components? Return the number of complete connected components. Okay. So I think the simplest thing here would be just to go through all the nodes. So if the node has no neighbors, that counts as a connected component. So how to go through all the nodes. So all the nodes are numbered 0 to n minus 1. So I can just go for, let's say, node in the range of n. If there is no neighbors, and I'll just shortcut neighbors with nays, no neighbors, then counts as a complete island. So so I can say here I have an answer that starts with 0, and if the length of the neighbor list or the graph at this node is 0, then answer is increased by 1 and continue. Okay, so that means at this point I'm dealing with nodes that do have neighbors, and I need to keep track of what I've seen. So seen is going to be a set. Yeah, seen is going to be a set. And I'm going to say that I'm going to attempt to see if this is a new island. This is a new complete component. So I'm going to say well, I don't know if I need this scene. I'm gonna I don't think this is necessary for this particular problem. So there's going to be a new island formed from this node, and we're going to try to see if it's a complete island. So we're going to start with this node. And so like if you start from any island or from any node in a complete island, then pretty much from that node you should be able to see everything else, right? And so if you add this node and all the neighbors to it, then you should have a complete island if that is complete. But if you add a node and all its neighbors, so let's say you start with 5, you add node 3, and that's your island. If you encounter anything that is if you encounter something that is not part of that initial set, like this 4, like if you traverse 5, traverse 3, and 3 you see 4, then you know it's not complete. So maybe I can say the start of the island is the node plus the array of the node plus the array of the neighbors to this node. And we're going to traverse everything in here, or we're going to go through all these spots and make sure that all the neighbors to these things are also within the start island. So I'm going to say the initial count is going to be just this So if this is a set, I don't want to do this multiple times. Like, don't want to do this multiple times. So like if I do 5 and I do 3, if I still need to do process 3, I need to process all the neighbors of 3. Seems like n squared complexity. So I think I'm going to go for every node in the start, for every k in start island. And then for every neighbor of k. For every neighbor in the graph of k, if this neighbor is not in the start island, then we know this is not going to work. So I'm going to say not complete is false here, and this is going to be not complete is true, and break. And then if we find that this is not complete, then we break the loop. And then if this is maybe this is we'll assume that it's complete is true. We'll set it to be false if we find that there is something that makes it false. And if it's not complete, then we break here. And after we go through all the nodes here, after this outer loop, if it is complete, then answer increases by 1. I think I can just return the answer at that point. Interesting. My output is 6. Oh, yeah. This node does need to be seen. Yeah, so we need to skip this thing. I guess seen could be just an array. So, so false for every n nodes. We'll say here that seen is true. Seen of this. So seen of this node is now true. No. When do I set the seen to be true? So if the node is unconnected, then I don't really care about seen. And if there is a connection here, I think seen should be set to true. And then I can say that for every node in start island, I need to set the seen of this node to be true. Okay, so if node is in seen, this is just going to skip this one. And k in start island, I can set the seen of this k to be true. I guess this is the same. What about my dead ends? So if it's not in start island, then this doesn't quite work. Or this isn't quite efficient, I think, but I think it should be workable. Okay, so it reduced the answer to 5, doesn't reduce it to 3. Alright, if complete, then I'll say print this node, complete node, complete island at, and then I'll just print out the start island. Else print not complete and this node. So complete island at 0, 1, 2 and 0, 1, 2. So I actually did it twice. So why did it do it the second time? Because it should have seen 0, 1, and 2. Oh, whoops, scene is not a map. It's a array of booleans. So scene, if scene a k, and okay, yeah. Scene of node, okay. Okay, so did the first one okay, and then the second one, it detected 3, 4, 5 as complete, which is not true. So 3, okay, so I think the issue is it first did node 3, which put 4 and 5 as part of the start island, which is correct. But then 5 needs to have exactly 3 and 4. The other connection. So I think here the requirement is the neighbors have to be part of Star Island, and it has to be exactly the same number of neighbors. So for each neighbor in the graphic, for k in Star Island, scene of k is true if the number of neighbors is not adequate. If the length of the graph k does not equal to, let's say, island size is going to be length of start island doesn't equal to the island size minus 1, then this is not going to work. Complete is equal to false. And then break. Otherwise, do this all the neighbors of this node. Okay, I think that should fix that issue. All right. Let's go ahead and just comment out this stuff. Turn answer. Oh, this thing. Don't think I need the else. Otherwise, it's going to have indent errors. Okay. So this logic seems a little inelegant. So scene of k is true. I think you need this thing in order for it to count correctly. That's fine. The start island is the set of the starting node and the neighbors to it. You assume it's complete. You get the size of the island. For every node of it, you're going to say you've also seen this node. And then for every, I think there's a slight, if the length of number of neighbors is not correct, then it's false. If the neighbors in the graph at k, for each neighbor of this node, make sure that neighbor is part of the island. And then if it's not part of the island, then you say that you're going to skip that at some point because that node cannot work as well. And then you say that this island is not complete. And then you break, and at that point, break the outer loop. And then if after you check a node it's not complete, then you break the outer loop there. And then after you go through all the nodes of your island, then you can say it's complete. I think this is all reasonable. Okay, I don't really see an obvious way of improving this. I mean, maybe you could use a while loop so that can break it more easily. For each neighbor in the graphic K. I mean, it's kind of funky because here you actually want to break the outer loop, which is why you need this if statement inside the outer loop in order to have this break actually break both loops. Is there a way to do that break without using this logic? For each neighbor, I don't really see it. Yeah. All right. Okay. Down to the summary of the algorithm. So for this one, it's just going to be create the graph mapping, 2D array or your default dictionary. And then for each node, assume that it's part of a complete island, which means that the whole island is that node and its neighbors. So once you make that assumption, you can traverse, go verify that by going through all the nodes of that set and checking for two conditions. One is the node that you go through, that verify that by going through all the nodes, where each node will have island size -1 neighbors, and 2, each neighbor is part of island. So if all the nodes of the island that you assume to be complete satisfies both those conditions, then if all nodes satisfy, then increment answer. Increment count answer by 1. Also increment if the node is isolated, which is there's no neighboring nodes to it. Alright, time complexity. So you go through all the nodes here, and for each node you're going through all the neighbors, and for each neighbor you're going through all its neighbors once. So I think it's let's say there's n nodes and e edges, and let's say m edges. I think because you have to go through each edge once to verify that that edge doesn't lead to a node that is not part of the island, then it has to be traverse everything once to check. So it'll be O of n plus m. you really don't go through multiple. You don't go to the nodes like more than twice. So like once when you like technically you might go to each edge twice, but I don't think you can do it more than that. And then for space complexity, this is going to just be, you have a 2D array. The 2D array size is going to be the number of edges. 2D array size is based on number of nodes and edges. So it's going to be like O of n plus n. Alright, cool beans. Pretty straightforward.